Hello everyone, my name is Divakar Ebape. In my final class project, I have developed a stock prediction app thanks to Professor Zoran, Rahul, and Blagoya. Without their guidance and direction, I couldn't have done it. My goal in this project was to create an application that can showcase and highlight the enormous power and endless possibilities of neural network. I chose to work with the stock market because it's challenging and something really hard to do. In the first part of the project, I explored and searched for different features and predictors that drive the stock price. Then I looked for different ways to collect data. Data is very restrictive, controlled by big players. Then I trained and tested my model with different feature sets. When I finally found my model, in the second part, I developed a web application that can make real-time predictions using that model. Why the stock price moves? It moves because of imbalances in supply and demand. If there are more buyers than sellers, then the stock will go up and vice versa. It's a constant tug of war between buyers and sellers. And also, buyers and sellers are always switching sides. News events are always breaking into the market. People's interpretation of these events are not same. People have different views, opinions, and ideas. So there is going to be always two sides, even though it's the same event. So there's always going to be this tension, and the price will always move in up and down motion. This is a real stock chart. I just rotated the axis 25 degrees. Now we can see the wave nature of the stock movement nice and clear. There are many ways to build a model. You can feed the network with actual performance data of the company like earnings, revenue, data from quarterly statement, and you can feed the network with prices, trading volume. These are called technical indicators to teach the model crowd psychology. The model will see the pattern and learn how the majority of the crowd behaves in a given scenario. So I follow the second method. Feature engineering. Price is the best feature or indicator. Besides price and volume, there are thousands of indicators people have been using for a long time. Most of them are derived from price and volume. So I have done a lot of research and decided to experiment with 5 or 6 indicators. I will talk about them briefly. RSI or Relative Strength Index. We have already seen stock price moves in up and down motion. These indicators tries to identify the peaks and valleys of the stock wave. This is the equation I used to calculate RSI. Then percent change also known as return. So we calculate it by subtracting previous price to current price. By doing so, we create a stationary metric that has constant mean and variance. This is the plot of the last 60 years of percent change data of Coca-Cola stock. We can see the same pattern repeating over and over. Model likes this kind of pattern. Log returns. When you take the log of percent change, we get log returns. This indicator tries to capture the exponential price movement that takes place every day in the market. When a breaking news hits the market, everybody jumps in at the same time to place orders. That makes the price go crazy. I didn't see much difference in my model using this indicator, but I think it's a good indicator for a highly volatile speculative stock. Market and sector influence. Before you buy a stock, you want to see what's happening around you. If all the stocks in the market going down for some reason, your stock is more likely to follow them. This concept is known as market influence. S&P 500 is an index fund made up of 500 US companies. I used it in my model to gauge market sentiment. Sector sympathy is the same concept. A good example is when all the electric vehicle and clean energy stock rose sharply after the election. Any stock in that category went up regardless of their financial situation. I got good results using these indicators in my model. I used LSTM network, a variant of RNN in my model. It can learn long-term dependencies and remember information for a longer period of time. It is widely used for time series analysis. LSTM cell users get to manage its memory very effectively. It knows very well when to forget unneeded information and add new information to its long-term memory called context. Data collection, you, you can get daily and weekly interval historical stock data for free. Shorter interval, 1 minute, 5 minute data is very expensive. So I use daily stock data of the last 60 years to train my model. When I have a base model, I download the shorter interval 1 minute to 5 minute data from different stock charts. You don't get more than 2 or 3 days of intraday data from those websites. So I store the data in a database and train my model every day. So I used Coca-Cola stock for training my base model because it's a stable consumer stock and doesn't have those wild price swings. It's easier for the model to learn. Now I will give a brief overview of some of the codes from my notebook. So after after I load the main stock data, Coca-Cola, using Pandas data frame, I calculate RSI and percentage on the opening price. So here I drop the first 14 rows because RSI calculation uses exponential moving average of last 13 data points. And then I load the market and sector data. For market, I use Spider, and for sector, I use XLP Consumer Staple ETF. I want to use opening price for these data sets. I join these data sets with the main stock data based on um, date key. All these three data sets have different date ranges, which creates a lot of null values. We have to drop all the rows that have nulls. So after joining, and this is the final data set. I split the data for train and test and validation. Okay, I put aside 6 months of recent data for testing. I use min-max scalar from scikit-learn to scale the data between 0 and 1. For features and levels, I slice the different to create as many smaller data sets as possible that contain 60 rows with increasing date time. The model has 60 time steps. At each step, the model is fed with a complete record containing all the features to evaluate and learn. Here I create a Keras sequential model with 4 LSTM layers, each containing 96 units. Then I add 20% dropout after each LSTM layer. I compile and train the model for 100 epochs. This is the loss plot. It starts to flatten after 8 epochs. I use validation loss as the key metric to compare different models. Testing, I create the test dataset applying similar processing methods I use for training dataset. After I get the predictions, I associate the prediction prices with the actual price and date time. This is the prediction data frame after processing. We can see the prediction prices with its corresponding actual price and date. This is the actual versus prediction plot. We can see the prediction prices following the actual prices very closely. So I use RMSE or root mean square error on the test dataset as the primary metric to determine the accuracy of the model. It tells us how far off the predictions are from the target price on average. This particular model has a RMSE test score of 0.63. The stock price fluctuates around 50, so the model is doing pretty good at guessing the future prices. Hyperparameter tuning, increasing the number of LSTM cells from 50 to 96. We get slight performance boost. Epochs count 100 seem to work best for training. The number of layers doesn't seem to have any measurable impact on the model performance. Continuous training and continuous testing. After selecting model, we have to continually train and test our model with new data every day. In the following section, I will discuss how we can develop an application and put our model to work. This is the application, this is the architectural block diagram of my application. The main components are Node.js, MongoDB, Chart.js, Python script, trained model. So on the user, from the browser, the user sends a request to the Node.js server. The Node.js searches MongoDB for predictions. If the predictions are too old, it calls the Python script. The Python script collects real-time data from public websites. Then it processes the data and creates a data frame and passes the data frame to to the model. The model creates a prediction and stores it into the MongoDB. Node.js picks up the prediction and serves the user with the prediction on a chart. So at the end, the user gets a chart, prediction chart. Node.js is a very popular framework for developing a web application. It's fast, it's lightweight, and very easy to work with. You can use JavaScript in both front-end browser and back-end Node.js app engine. Here are some of the instructions for installation. I use MongoDB as the main database for my application. MongoDB is a document-oriented database, and it's great for transactional queries. It's very fast. Here are some of the installation instructions and configurations, initial configurations after installation. Here are some of the schemas I used in my application, MongoDB schemas. Python script. So in the Python script, I used request library to make HTTP GET requests to collect real-time stock data from online stock charts. The HTTP response is a JSON object. So I parse the JSON object to create a data frame. So once I have the data frame, I apply the same data processing steps I used for training the model. Then I load the trained model to get prediction and process the predicted data. And then I store the predictions to MongoDB. Chart.js, I use Chart.js to create charts on the browser. Chart.js is a very light JavaScript library, and you can render beautiful responsive chart. And it's very easy to embed Chart.js library in the HTML. This is the user interface. This is what you see when you open the application on a browser. You can select stock. You can select a stock and time interval from the drop-down menu. Also, you can pass in a number in the max data point menu to specify the maximum number of data points you want the prediction for. This is the Tesla stock prediction on 12/7 pre-market hours. The blue line is the actual price. The red line is the predictions. The prediction is indicating strong upward momentum for Tesla. This is the Tesla chart a few hours later, and it did show that Tesla went up a lot that day. The model proved to be correct on this occasion. This is the workhorse stock prediction in afternoon of 12/8. You can see the predictions are closely following the price, the actual price. That's it. Thank you so much. If you have any questions, please send me an email or contact me at LinkedIn.